Here we have a problem where we have a block that is tied by a rope, and that rope is wrapped around a hoop, and that hoop is fixed by some axle in the middle there. This block is 1.5 meters above the ground, and it's going to be released. We can imagine that when it's released, it's going to accelerate downwards, and it's going to move downwards, and eventually it's going to hit the ground there. And we want to find the block speed just before it strikes the ground. What we can see from this problem here is that as the block falls, it's going to pull on the rope. As that rope pulls, it's going to cause the hoop to rotate with it. We can imagine that hoop is going to have some sort of angular motion. As it rolls, it's going to unspool the string and let the block fall to the ground. So we're trying to find the speed as it covers this distance. You can kind of see here how, if we're talking about rotational motion and this block, we have its mass. So we should be thinking in terms of rotational dynamics. That's how we're going to treat a system here where we have rotational motion and linear motion. They're connected by a rope that carries tension, which is a force. And so when we're talking about forces, we're going to consider that. If we're trying to find the speed at the end of falling some distance, you can imagine that looking at dynamics is going to give us the acceleration of the block. And once we know the acceleration, we can find the speed that it has. In this instant here, just as it's about to reach the ground, it's going to have some speed right as it's about to hit the ground, and that's what we can find there. So in order to pursue this problem, we're going to follow the steps of rotational dynamics. We already have our picture here. We're going to see our objects of interest. In this case, we have a hoop and the block. They're connected together, so they're both objects of interest. This hoop here is a rigid object. It's got some axle in the middle, and so it's going to have a fixed axis of rotation there. That axle is also going to provide a normal force to hold the hoop in place in response to any other forces that are acting on it. As far as forces go, we can do a force identification for the block. The only point of contact we have is the rope, and so we're going to have a tension associated with that rope. This block is also going to have a weight. That weight is going to act at the center of mass of the object, and we have the weight pulling down on it. So with the block there, we're not really worried too much about it. We can think of it as essentially a particle. When we look at the hoop, we have a point of contact here with the rope. The rope is always going to pull towards the center of the rope, so it's going to pull off of both sides. Note that this distance here is going to be r, the radius of the hoop. The hoop itself is going to have its own weight, and it's going to have a normal force from the axle there, but you can imagine that those two are going to end up canceling each other out. We know that from our previous analysis that the block should accelerate downwards. The hoop should have a clockwise acceleration, but we can also say here that the acceleration of the hoop should be 0, that the hoop itself is affixed with some sort of axle, so it's not going to move anywhere, it's going to spin in place. And so what we can say here, based on this relationship that we have between these two, we can say that our constraints are going to be that the speed of the block, the speed of the object as it falls, is going to be r times omega. The speed of the block is the same as the speed of the rope, which is the same as the speed of the outside edge of the hoop, which is our tangential velocity there. We can also say that the acceleration of the block as it falls is going to be r times alpha, the angular acceleration of the hoop, and the radius of the hoop there. For the sake of simplicity, I'm going to drop the subscripts for those. I'm going to use v and a for the block, and I'm going to use omega and alpha for the hoop. My next step is to use Newton's second law in linear and rotational form. Linear form for the block, rotational form for the hoop. Looking at the block, we'll draw a quick sketch here. We can treat it essentially as a free body diagram. because we can treat it as a particle. We have the weight of the block pulling down, we have tension pulling up, and the block itself is going to be moving downwards, and it's going to be accelerating downwards. So I can use Newton's second law. There's really only forces in the y direction in this case. I'm going to ignore the x direction because nothing's happening horizontally. And I can say here that the forces in the y direction are tension that's going up and the weight of the block, which is going down. We have the mass of the block, and then I have the acceleration of the block, and the acceleration of the block is negative. Remember that this right here, these are the magnitudes, but you still need to include the direction with a negative sign, if necessary. I try to put a negative or a positive sign to always remind myself. Looking at the hoop, we also have forces acting on the hoop, but since the acceleration has to be zero, basically the normal force is going to cancel out all the other forces. So there's going to be zero net force acting on the hoop. However, the hoop should be rotating, so there should be a net torque, and we can find that. Here is the hoop. There's its axis of rotation. We know that the tension from the rope is acting at the outside edge. The weight of the hoop is pulling down at the center of mass, which should be at the center of the hoop, at the geometric center. And there's going to be a normal force essentially from the axle there. So I can look at the torques that I'm going to have. I'm going to have a torque from the normal force, a torque from the weight, and a torque from tension. But notice here that the weight and the normal force are both applied at the axis of rotation, at the axle there. So these are both going to be zero. Neither of these are going to contribute any motion to what we've got here. If I look at the tension, my torque is going to be RF sine of phi. So the torque for tension is going to be R, which in this case is little r, or is going to be capital R, the radius of the hoop. The F in this case is capital T, the tension, and in this case we extend our radial line, and phi goes from the extension of the radial line to the direction of the tension vector. That is a 90-degree angle, so I'm going to have sine of 90 degrees there, because phi here is equal to 90 degrees. Sine of 90 is just 1, so that's not going to do anything for us. This tension is pulling this way, that is the clockwise direction, and so that's going to be a negative torque. The total torque there is equal to I times alpha. Alpha is the magnitude of the angular acceleration, and we said that based on this picture, we should be rotating clockwise as well, and so our acceleration should also be a negative quantity. Notice that those would end up just canceling for us. We can also say that the moment of inertia for a hoop is mr squared, because all of the mass of the hoop is concentrated all at a distance r from the axis of rotation. That's a value that you can get off of a table of moments of inertia. Notice that I used a capital M here for the mass of the hoop to distinguish that from little m that I was using for the mass of the block there. A couple other things that happen very commonly. R and R cancel. I've got an R squared, so R squared is R times R. I can also look at these two terms here. R times alpha is the acceleration of the object. And so I can go ahead and say here that the tension in the rope is the mass of the hoop times A, the acceleration of the block. So what I have here are two equations. I have an equation for the block. I have an equation for the hoop. These two tensions are an action-reaction pair. They're basically the two ends of the rope. What I'm going to do is substitute one into the other. I'm going to substitute in W is mg. That's the weight of the little block. I'm going to add mg to the other side and make these go away. I'm going to add ma to the other side and make these go away. I'm going to end up with ma plus little ma equals mg, or mg is equal to m plus little m a. Notice this follows the same format that we've seen before. This is basically the net force, the total force driving the system. The whole system is being driven by the weight of that block. This is the total mass that's being driven by the system. The total mass is the mass of the block which is moving, and also the mass of the hoop which is being driven due to the rope applying part of the block's mass. This is technically the moment of inertia. It's just that for a hoop, the moment of inertia gives us this value. And so I can find the acceleration. And I found the acceleration here. I'm giving myself extra significant figures. This is an acceleration, and so that should be measured in meters per second squared. That is what dynamics gives us, right? We use dynamics to talk about weights that come from masses, and use forces like weight, like tension, to find acceleration. We see here that the acceleration is a constant value, and so if we know that the acceleration is constant, we want to find the final velocity. The second step of our problem here is to use our constant acceleration equations. In this case here, the block is released released from rest, is implied. The acceleration we just found is 5.945, and we're going to call that negative because it's accelerating downwards. It's moving 1.5 meters downwards, so our displacement is actually going to be a negative value as well. And we want to find the final velocity here. We have an equation that will get that for us. Once we've written out the equation, we can plug our values in and solve. Whenever we have a velocity here, the velocity should be measured in meters per second. We always get a plus or minus whenever we are doing a square root, which is what we did there. And so in this case, we know that we're moving downwards, and we know that the velocity needs to be negative so that we're moving downwards, which is consistent with what we found. We also used way too many sig figs to try to avoid rounding errors. In this case, we go back, we see we've got 3 sig figs everywhere, so we're going to end up rounding this to 3 sig figs also, and our final velocity here should be negative 4.22 meters per second. That's the speed just before the block hits the ground.